Hello, my name is Ryan, and in this video we're going to be going over a specific heat experiment. Basically, I'm going to be going over the data, and I'm going to be going over the results of the experiment. So for the overview of the experiment, we're basically going to have three different materials. We're going to have steel, which I got from Ace Hardware, and we're also going to have copper, essentially a copper tubing. And then this would be a steel ball, both from Ace Hardware. And then I also made this aluminum ball from scratch. I just got some aluminum foil and put it together and formed it into a little bit of a ball. So an aluminum ball. And then to conduct this experiment, I basically submerge the different materials into a boiling hot water. So we get the temperature of the different metals up to 100 degrees Celsius. Then I put the metal into a beaker of volume that we've already measured. And we also know the weight of the metal. We've already measured that as well. And then so we submerge that in the water and we see what the difference in temperature is. And basically, from this, we are trying to find the specific heat of each different metal and see how accurate we can be. And we use the formula Q is equal to M times C times change in T. The good thing about this is the change in heat transfer is going to be the same in magnitude for the water and for the metal. So we can set these equations equal to each other. So we can say M of W, which is water, the mass of the water, times the specific heat of the water, times the change in temperature of the water, and that is going to be equal to the mass of the metal times the specific heat of the metal, and also times the change in temperature of the metal. Then we can rearrange this formula and get independent and dependent variables, and also a slope. We can set the change in temperature of the water equal to M, the mass of the metal, times the specific heat of the metal, all over the mass of water times the specific heat of the water, times change in T over M. As you can see, this is getting us into our y equals mx plus b formula. So this would be our y variable. This would be our slope. So this would be like the m. This would be like the m, and this would be like the x. And then you're probably wondering, how will we find the specific heat of the metal then? Well, this isn't too bad. We'll find the slope. We'll get the slope is equal to the mass of the metal times the specific heat of the metal, all over the mass of water times the specific heat of water. We'll multiply both sides by the mass of the water and the specific heat of the water, and divide it by the mass of the metal, and these are all knowns. We divide it by the mass of the metal times the slope, and then this will give us the specific heat of the metal. And if we do this right, we should get a very close approximation to what they say online. So basically, as you can see in the formula, we're basically going to be graphing the change in T, the temperature of the metal, to the change in temperature of the water. And we'll get this slope that looks something like that. Okay, now let's measure the mass of the materials. This is an aluminum ball. It weighs 54 grams. Now let's measure the copper pipe. The copper pipe weighs 12 grams. Now let's measure the steel bolt, and the steel bolt weighs 38 grams. The mass of the empty beaker is 35 grams, and the mass of the beaker with water is 84 grams. This is trial 1 of the steel bolt. Basically, the air temperature right now is around 21.8 degrees Celsius, and now I'll get the temperature of the water. I'll just let it sit there for a second. So basically, for this steel bolt, we're going to take that water, which is at 100 degrees Celsius since it's boiling, and the steel bolt will also be at 100 degrees Celsius. Since that's water it's been in for about 5 minutes, I'm going to bring all that over here. I'm going to use my tongs to take it out, put it into there, and then I'll record the temperature of this. So the temperature of the water right now is 28.3 degrees Celsius. Okay, nice. And now I'm going to take this, bring it over here, Use my tongs. Shake it off to get the water off. We'll put this in. And now we'll take the temperature of the water. I'll swirl the water around a bit to make sure it's all moving. Right now it's at 32 degrees. It looks like it's still increasing. 34 degrees. Wow. 34 degrees might have been the max. It looks like it's dropping now, 32.5. So it looks like 34 degrees is the max. The mass of the empty beaker is 35 grams, and the mass of the beaker with water is 93 grams. This is trial 2 of the steel screw. So the air temperature right now is 22 degrees Celsius. The water temperature, let's check the water temperature. Yeah, it looks like it's around 27.3 degrees. Okay, now let's put the screw in. Okay, yeah, it looks like 31.8. The mass of the empty beaker is 35 grams, and the mass of the beaker with water is 88 grams. Okay, this is trial 3 of the steel bolt. Right now, the air temperature, it looks like, is around 22.7 degrees Celsius. Right now, I got a little bit of colder water on this one to see if this changes it up at all. This is around 20.5 degrees Celsius. 20.5 degrees Celsius. It's hovering around 25.6 right now. The highest was 26.3, but that might have been because I touched the screw. So let's take the 25.6 degrees Celsius. It's probably our best bet. The mass of the empty beaker is 35 grams, and the mass of the beaker with water is 82 grams. This is trial 1 for the copper pipe. Right now, the temperature of the air is 20.5 degrees Celsius. The temperature of the beaker is 25.6 degrees Celsius. 27.1 degrees Celsius is the max temperature that's got to. The mass of the empty beaker is 35 grams, and the mass of the beaker with water is 76 grams. This is trial 2 of the copper pipe. The temperature of the air right now is 20.6 degrees Celsius. The temperature of the water is 25.7 degrees Celsius. Bring this over. We'll pull the copper pipe out, shake the water off, put it into the beaker, swirl it around to get all the water in contact with it. So it's still 27.1, so I think the max temperature was 27.2 degrees Celsius. The mass of the empty beaker is 35 grams, and the mass of the beaker with water is 82 grams. This is trial 3 of the copper pipe. The temperature of the air is 20.7 degrees Celsius. The temperature of the water is 24.1 degrees Celsius. Yeah, it's not changing anymore. So 25.5 degrees Celsius is our max temperature. To be able to fully submerge the aluminum ball, we needed a 100-gram beaker, and the mass of the beaker with water is now 270 grams. Okay, this is trial 1 of the aluminum ball. Right now, the temperature of the surrounding air is 20.6 degrees Celsius. The temperature of this water, yeah, looks like it's around 28.1 degrees Celsius. Get the water off. Plop this in. I'll have to hold this down while we do it. 32.2 degrees, and it's dropping now, yeah. So it looks like 32.1 now. So we'll take 32.2 degrees Celsius. Okay, this is trial 2 of the aluminum ball. Right now, the temperature of the air is 22.2 degrees Celsius, 22.1 actually. The temperature of the water is 21.3 degrees Celsius, and it's not changing. Nice. Okay, now I'm going to put the aluminum bowl in. We'll bring this over. The water's boiling, and it's been in for about 5 minutes, and then I'm going to just let the water get off. It looks like it's staying at 20. Oh, now it's at 27. Now it's at 26.9. So it looks like around 26.9 to around 27 degrees Celsius. This is trial 3 of the aluminum bowl. Right now the temperature of the air is 20.8 degrees Celsius. Let's measure the temperature of the water right now. And the temperature of the water is 28.9 degrees Celsius. The final temperature is 34.6 degrees Celsius. Okay, now for the analysis. So I put all our data into a table. I put the change in temperature for the metal, the change in temperature for the water, the mass of water, the mass of the metal, and I put it all into a table. And then I calculated the specific heat of the metal. You're probably wondering how I calculated this. It's basically, as I said earlier, you can relate the two equations to each other because the Q is equal for both the metal and the water. So Q is equal to M times C times change in T. So we can set M of the water, the specific heat of the water, times the change of the temperature for the water is equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. Then from this we can get the specific heat of the metal all by itself. We can basically just divide the mass of the metal. So we'll keep this, and we'll just divide the mass of the metal, and also divide the change in temperature of the metal. And then we get the specific heat of the metal. So basically, we just plug in the values. We have all of these values. The only one we're missing right now is the specific heat of water. But the specific heat of water is just 4.184. 184. The units are joules per grams times degrees Celsius. So I plugged in that. I got all the values here, the specific heats, and then I averaged them out for each metal. And then I used this average and plotted them into this table here. So that's all the averages of the specific heats of all the metals. And then you can see this graph here. So you can see steel ball is around 0.429, copper pipe is a little less, and then the aluminum ball is quite a bit more. And then the incredible thing here is that this is the actual data. This is the actual data, and do you see how similar it looks to this graph and this graph? It's almost identical, which is incredible. The only two values, they're only off by a little bit, by very small amounts. So it's incredible how accurate we were able to get on this experiment. If we dive into this a little bit more, you might wonder, hey, the copper pipe and the steel bolt here are a little bit of a lower guess to these two. I had the same thought, and basically I was thinking maybe when we take out the metal, the metal is exposed to some of the air, and then maybe some of the heat energy is given out there. And what would this do? This would cause the change in temperature of the water to be less. And if we look back at our equation here, if the change of the temperature of the water goes down, then the specific heat of the metal would also go down, and it makes sense that these specific heats are slightly lower for this table, for these two values, than these two values. But you see the aluminum ball is actually an overestimate from this right here. The reason that I suspect for this is that the first trial, you can see that the first trial here, the specific heat is actually around 0.8, so it's actually quite an underestimate. And then it jumps all the way up to this 1.08 value and 1.01 value, so it's a very similar value. And I suspect what happened was water came into the tiny air pockets in my aluminum. When I tried to squish it together, but there's still air pockets, and the water probably was able to get into there. So if the water is able to get in, the water has a higher specific heat, as we saw. The specific heat of water is around 4.148, I'm pretty sure, or 4.184. And this would cause the overall specific heat of the aluminum plus water to be greater, causing it to be this overestimate here. And that is my analysis. Thank you for watching the video.